All right, this is your first podcast on chemical equilibrium. Chemical equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. Now let's see what I'm talking about. So our first podcast is going to be over the nature of chemical equilibrium. This is going to get you the concepts you need and some of the mathematical problem solving that we're going to need to do in order to get through this unit. So let's get started. So we had some previous thoughts on chemical reactions. Before the reaction, we assumed that 100% of our substances were reactants and 0% of our substances were products. And after the reaction, we pretty much assumed that all of those reactants turned into products and we had no more reactants left and all we had was products. But we have new thoughts that we need to think about with chemical reactions. We have what we call a forward reaction where the reactants are decreasing and the products are increasing. So as the reaction proceeds, the reactants are going away and the products are forming. But once we form some products, there is a chance that there is a reverse reaction happening where those products can reform back into reactants. So in the reverse reaction, the products are decreasing and the reactants are increasing. So that's kind of weird for people to understand. So I wanted to make sure you saw that. Because of this new thought we have on chemical reactions where there's a forward reaction and a reverse reaction, when we write chemical equations that are in equilibrium, we say, we use a new equation that has a different type of arrow, showing that there is a forward and a reverse reaction. Here's a graphical analysis of chemical equilibrium. Notice how the forward reaction rate decreases and the reverse reaction rate increases. Now, in the end, the reaction rates of the forward and reverse reactions are exactly the same. Notice I said reaction rates, not reaction concentrations, because they could have different concentrations, but the rate of forming products and the rate of forming reactants is equal. This is what we call equilibrium. Now, this is the major concept of this unit, and it's going to be our major calculation steps for this unit. What I see here is a chemical equation that has A plus 2B yielding 3C plus 4D. Notice the new type of arrow that I've put in here. So we have reactants on the left and products on the right. Now the law of mass action, which helps us calculate our equilibrium constant, is shown by putting products over reactants. And if you look here, C and D are our products, and they are raised to the power of their coefficient. A and B are our reactants, and they are also raised to the power of their coefficient. Notice that products are on top and reactants are on bottom. You'll also notice that they're on brackets. What brackets mean, essentially, is that we want their concentrations, which is usually molarity. So now that we see that this works, I got a simpler equation here for you. Just A plus B is reactants and C plus D is products. So what we're going to do is we're going to use that law of mass action here. Just C times D, concentrations, divided by A times B, concentrations. What we can determine from this is our equilibrium constant, or KEQ, has certain values that we need to know. At equilibrium, if KEQ is greater than 1, it means that the product's concentrations are more than the reactant's concentrations. Think about it. The C and D would have a larger number than A and B, which would make a number greater than 1. But if the reverse is true, the reactants are more than the products, then our KEQ is going to be less than 1. We're going to have a larger number on the denominator than we would on the numerator, which would give us a value less than 1. If the reactant concentrations and the product concentrations are exactly the same, then our equilibrium constant is equal to 1. So now we can determine where equilibrium lies in this equation. Is it going to be favoring the products or is it going to be favoring the reactants? If KEQ is greater than 1, we're going to see more products than we are reactants after the reaction is complete. If KEQ is less than 1, then we're going to see more reactants than we do products after the reaction is complete. So here's a sample problem calculating KEQ. Let's look at what we have here. At equilibrium, the concentrations are found in the table below. Calculate KEQ for the reaction and tell whether the products or reactants are favored. So look at our concentrations down there. We have A plus 3B yields 2C. And our concentrations at equilibrium are given in the table there. So let's take a look at the law of mass action. Notice our product concentrations are on top and our reactant concentrations are on bottom. And when we perform this calculation in our calculator, we end up getting a KEQ equal to 1.3. All right, take a look at that and make sure you understand how it works. And now we can actually determine whether the products or reactants are favored. Notice that KEQ is greater than 1. When KEQ is greater than 1, then the products are favored at equilibrium. So we would say that this reaction favors the products and equilibrium lies to the right of the equation.